We're going to be starting our next unit, which is all about waves and the electron. We're going to kind of tie them together as means of energy. So we're going to start with our discussion about waves and then eventually link electrons to that. Waves, as we can see in this picture, is kind of this up-down motion. We'll describe parts of a wave momentarily. But waves transfer energy from one location to another. If you think about the waves that you normally think about, like ocean waves, they are moving energy throughout the water. They're characterized by three main parts: frequency, which is this little Greek symbol nu here, basically a V; wavelength, which is an upside down Y, which is the Greek letter lambda; and amplitude. You can use F or W if you prefer for those symbols, but I will be using those when I'm discussing it. We can see here that waves are going to be part of our electromagnetic spectrum. Electromagnetic spectrum here is going to tell us about all of the waves we see here from radio to gamma. You can tell that we start with really long waves and then they become a lot more consolidated at the back end of that diagram. And that correlates to kind of our definitions of wavelength. So the length being from like one crest to another crest, one peak to another peak. And then this is the distance of that like span of the peak to peak. And so as we go across, these get smaller. And then we'll see the relationship between frequency and waves when we are discussing parts of a wave. So we're going to start with this idea of what is light, what is energy. So the speed of light is a constant. Speed of light is always going to be 3 times 10 to the eighth meter per second in a vacuum. It moves a little slower in air, it'll move a little slower in like water and things like that. But in a vacuum, it is that speed always. Going along with that, we're going to have something called Planck's constant. Planck's constant is going to be a consistent number we have of energy for a packet of light. So we have 6.626 times 10 to the negative 34. And we'll put some units on that in a moment. But again, this is kind of our packet of light energy in joule per second. And so these two equations are going to be related as such. We're going to have our speed of light. Again, this is 3 times 10 to the eighth meters per second is equal to the wavelength times the frequency. When we get into parts of a wave, we'll kind of explain how that makes sense a little bit more. And then we're also going to have that the energy of the wave, we'll label these a little bit more: wavelength and then frequency, is equal to Planck's constant times frequency. So here we have that number. Again, that's a constant, and then this is again frequency. When we're thinking about these equations, you'll notice they have one variable in common rather. This is the frequency. So whenever we are trying to solve for energy, if given a wavelength, we're going to need to do two equations, which we will look at when we start doing our math. But it is important to note that if we want to solve for energy or wavelength, those are in separate equations if given one and wanting to find the other. So you'll need two equations. So in terms of all of our information, this is kind of what we know. Now, the relationships are going to be as follows. As we see here, the speed of light is a constant. And because these are multiplied, these are going to be inversely related, meaning if we have a high wavelength, we should be expecting a low frequency. This is an inverse relationship. So again, we're expecting, if we look back at our chart, if we have a high, aka long wavelength, we're expecting a low frequency. So you can see this is a lower number than over here. Oppositely, if we have a short wavelength, we're expecting a high frequency. And that is because this picture of the wave, it's moving at the same speed. And so the frequency is how many waves are passing at a given time. If we look at this, right, we're going to have less waves passing when the wavelengths are longer than we're going to have when they're shorter, because the entire thing is moving at the same speed. So it makes sense that it is inversely related. The longer your wave, the less waves pass, therefore the less frequent it is. In terms of energy and frequency, these are going to be directly related. As you can again see, we're expecting that because waves transfer energy, the more waves that pass, the more energy transferred. And so something where we have a high frequency, we're having more waves, and so more energy transferred, which should make sense because gamma, as we learned about in nuclear, is very harmful radiation. And you can kind of think about all of this on this side, where it's kind of the more frequency wavelengths, that it is more harmful radiation, right? Ultraviolet, you need sunscreen, X-rays, you need a little lead vest when you go to the dentist, versus like a radio wave, that is literally what they use for the radio. We're not concerned about that. We're using it for communication things. And that's because it is not as much energy and the wavelengths are so much longer that it's really not nearly as harmful to us. So further defining our parts of a wave here, we're going to start with the top of the wave. This is called the crest. The crest or the peak. Um, the wavelength here can kind of be measured two ways. You can measure it from basically one full wave, one up, one down. So you can measure it from the origin, from kind of point to point, but typically we define wavelength as the distance from a crest to a crest. But this can also be considered wavelength. The amplitude here is the height of the wave. In terms of energy, it is less important. It is more about kind of the intensity of that. So if we're thinking of waves as like colors in the visible spectrum, a higher amplitude wave would be a like more intense color of a wave. So it's not really that important for kind of what we care about, but it should be displaced upwards as much as it's displaced downwards. And then, as I said, G here is kind of the origin. That's kind of the center part of your wave. And then lastly, we have D, that is the trough. That is the bottom-most part of your wave. This is a transverse wave. You'll talk about other types of waves when you get into physics, but this is the mode of transport of a light wave. And this, if you've taken the correct math at this point, this should be identifiable to you as a sine wave. So you can kind of see that there. So nodes are going to be kind of what I've already colored here. This is where they go through the origin. And then the peaks of the waves or the troughs of the waves are antinodes. This is kind of the maximum displacement from the origin. That won't be that important, but it's again just kind of speaking to the amplitude and identifying the nodes helps relate it to electrons a little bit. So we should know waves carry energy from one place to another. The highest point of a transverse wave is called the crest, while the lowest part is the trough. I always think of that as like a horse trough where you're like drinking out of it. So it's like the bottom part. The amplitude is the height of the wave, peak. The distance from one crest to the next is the wavelength. And then if we're looking at these, how many loops does each wave have? I'm going to say this is 1, 2, 3. This is 1 and 2. This is 1, 2, 3, 4, 5. And this is 1. Which wave has the greatest energy? Again, we're assuming they're all moving the same speed. So I'm going to say the one that has the most loops is going to be the most energy because it is the most frequent. As we go back to our equations really quick, one relationship, because they're in separate equations, that is not listed here, that I'm just going to kind of include based on a sort of like transitive property here, is that energy is inversely related to wavelength. Because energy goes up as the wavelengths get closer, right? Long wavelengths over by the radio is going to be lower energy. And then as we get a shorter wavelength, we're expecting, again, that number to go down. And energy should go up because they become more frequent. So that'll finally lead us into our idea of the math. Again, we have our two equations. We have our constants here. And when we're solving these problems, I'm going to do a few examples before you have to try on your own. When we're solving these problems, you are going to really have to focus on what you're given. If you're given two of the things in, or asked to find one of the things in any of the equations, given the other, you just need the one equation. However, specifically, if you are given one of these circled things and asked to find the others, you will need to use both equations. So let's start. What is the wavelength of radiation whose frequency is 5 times 10 to the 15th seconds? So in terms of units, we're expecting wavelength is in meters. And if it's not, we must convert because this is meters per second. Frequency has a few different units. They're all the same, but they're represented differently. Officially, frequency is 1/seconds. So how many waves pass per second, essentially. Sometimes that may be written as S minus 1, which is the same thing. It just means seconds is in the bottom in that case. But often it is called the name of that, which is hertz. That's like the official name. So all of those are interchangeable units for frequency if you see those. And then energy is going to be in joules. So we will need to pay attention a little bit if things are needing to be converted, if they're not in meters or hertz. There are a few like where it's like megahertz or things like that. You will need to do some dimensional analysis. So we're going to start, this is wavelength, this is frequency. So I can use this first equation, equation 1. This equation is pretty straightforward because again, we always know this number. In this case, we're looking for wavelength. We have 5.00 times 10 to the 15th. So we will always solve this equation the same way because of the fact that 3 times 10 to the 8th is on the left. Whichever one we are trying to find ends up alone, and then the other one that we have gets divided over. So in this case, we end up dividing over the frequency because we want to end up with wavelength by itself. So take a moment, type that in your calculator, and come up with your answer. And make sure to put the correct units on that as well. We want to make sure that we have consideration for what our units for each of these things should be. And then also consider sig figs. If we did that right, we should have, in this case, 6.00 times 10 to the -8th meter. And you can kind of check if that makes sense if we go back to this chart here. If we look 10 to the -8th, 10 to the 15th, those kind of align right here, right? And so that is a logical kind of calculation. Okay, another one here. So notice this is now in nanometers, which is a pretty common unit that you'll see for waves. So once we do like one conversion, it's going to be somewhat consistent. This is the reversal of what we just did. So again, we're using the same equation because both of these things end up in the same. So 3 times 10 to the eighth. In this case, we have 670 nanometers, but we need to get that to meters. 10 to the ninth nanometers is 1 meter. So this becomes 6.70 times 10 to the negative seventh meters. And again, as I said, whatever we are solving for ends up alone. So in this case, frequency is over here. And then we end up dividing by the other number we had. You want to make sure you are using your E button or putting this bottom number in parentheses. This is the mistake a lot of students get into, that their calculator divides like the 6.7 part, but then ends up multiplying the negative 10 to the negative seventh if they don't use the correct buttons on their calculator. And so it's important that you, one, recognize that your exponent makes sense, but are very intentional about how this is getting plugged in. I'm going to do 2 sig figs for this one, so 4.5 times 10 to the positive 14th. Again, you can check. Positive 14, negative 7. Yes, that makes sense. Okay, number 3 is going to be our other equation. We have a frequency here, and we're looking for energy. Again, these both end up in the same equation, so we only need one. It just happens to be the other one. This one is a little easier in terms of how we have to solve it, because sometimes we are just multiplying, like in this case. So we have our 6.626 times 10 to the negative 34th, and then 2.22 times 10 to the 14th. And so when we need to find energy, energy is already isolated. So all we're going to have to do there is simply multiply these two numbers. This one you have to be not quite as careful because you're multiplying in terms of using the E button, because when you're multiplying, you don't run into the same issues necessarily. Sig fig wise, we're going to want 3 sig figs. So this should be 1.47 times 10 to the negative 19. And then energy should have units of joules. I forgot to put a unit on number 2. Number 2, because it is frequency, we can just put hertz. Box off my answers a little bit here. I'm going to do one more example, and then the rest of them will be yours to try. So we want to look for one where it is asking about having to use 2 equations. So I'm looking for one where we have energy and frequency. Here we go. Number 13. So what is the energy of a photon with a wavelength of 827 nanometers? So energy, as you recall, does not exist in the equation with wavelength. So the first thing I'm going to want to do, kind of divide my work in half here, is solve for the frequency. I know that this is going to be 827 nanometers, but again, I need to convert my nanometers. So 10 to the ninth nanometer, 1 meter. And so this becomes, if I kind of plug everything in, 3 times 10 to the eighth divided by 8.27 times 10 to the negative 7. And that answer, kind of put it down here, is my frequency. But that is not the end of my problem because I do need to make sure that I can plug that into the other equation because this only solved for frequency. I'm not going to round yet, so 3.6275 blah, 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 times 10 to the 14th. Energy is what I'm looking for. I always have H. And before I didn't have frequency, but now that I've solved the other equation, I can plug that number in for that. And so I end up taking 6.626, wrote that backwards here, 626, times 10 to the negative 34th, times my answer from the previous problem, so 3.62 whatever, times 10 to the 14th. And then finally, that is going to give me my answer, which is going to be 2, for sig figs, 2.40 times 10 to the negative 19th joules. Just be on the lookout for that. You can also see some of these, we have like megahertz. You will need to process conversions. Okay, the rest of the time will be yours to work on trying to do the rest of the problems.